So let's look at the last page that we had up last time here. We had two possible resonance structures of this molecule with C in the middle, O and two chlorines attached to it. We got to the point where we could choose whether to make the double bond to the O or the double bond to one of those chlorines. And the way we choose which is sort of the better structure here is with those formal charges. And a formal charge is just sort of like a electron counting tool. It sort of tells you if something is a formal charge of 0, that means that that atom is sharing the normal number of electrons that it would normally like to share. Okay? But it's possible to make covalent bonds by sharing extra electrons or by sharing not as many electrons, and that's where these formal charges come in. So the structure on the left, the carbon that has 4 bonds, the chlorines that have 1 bond, the O that has 2 bonds, those are all 0 formal charges. Okay? And remember, the quick and easy way to count formal charge is to start with the valence electrons from that original atom, like the chlorine there, if we start at 7, and then just count backwards for every mark that you see around it. Okay? So subtracting 1 from every dot, and essentially subtracting half of the shared electrons, but that just means subtracting 1 from that line that's there. Okay? So if we just do 7, 6, 5, 4, 3, 2, 1, 0. Okay? So 4, 3, 2, 1, 0. So atoms that have 0 formal charge, those are sort of the atoms that are bonded in the most common way. And if you had an introductory chemistry class or something like that, a lot of times you're just only taught the normal way that things bond. Like, for instance, chlorine making 1 covalent bond, or O making 2 bonds, and carbon making 4 bonds. Okay? But the reason that's sort of the most common way those things are bonded is because that's what gives them 0 formal charge. Okay? That's what allows them to start with their existing number of electrons and share electrons from an adjacent atom to get them up to 8. Okay? But look at this other structure over on the right here. We have an O with 1 covalent bond. It still has an octet, right? Because it's got 2, 4, 6, 8. So it still has 8 electrons around it, okay? Which is fine. But in this case, if we do 6, we get 5, 4, 3, 2, 1, 0, minus 1. So that O has a minus 1 charge, okay, which essentially means that O has a bit more electrons around it than it normally would. And you can see that totally compared to this one. An O with 0 formal charge has 4 unshared electrons, and then 2 of its own electrons involved in bonds. Okay? This one has 1, 2, 3, 4, 5, 6 electrons on it, okay, plus actually another electron that's part of that covalent bond there. So it sort of has, so it's rather than sharing more, okay, it kind of has more to itself. That's where that negative formal charge comes from. Okay? But those formal charges will appear on atoms that look different from their normal bonding pattern. Okay? That O with a single bond is a minus 1. That chlorine that's made 2 bonds, okay, compare this with the chlorine with 0 formal charge. Okay? This chlorine that just has 2 lone pairs and a double bond there, that's a plus 1 formal charge. Now notice the octet rule is still met on all of these. Okay? That's very important. We're going to sort of first look at the octet rule, okay, in that each atom has 8 electrons around it. People start sort of forgetting about the octet rule, okay, but the octet rule is very important. We are going to expand our octet in a little bit, but only under certain circumstances. So you should always be first starting out with octets, okay, to make absolutely sure that everything has 8 around it. So everybody sees the 8 electrons sort of around each of those atoms, right? That's very important. But then you do the counting backwards from its valence electrons to give formal charge. Okay? That sort of gives an idea of how much charge has built up around that atom as a result of that particular bonding pattern. Okay? So over on the right, that O has a little extra minus charge. That chlorine has a little less charge because it's sharing more electrons than it normally would. Okay? So the major contributor towards this molecule is the one that doesn't have formal charges. Okay? So let's actually write here the actual molecule more closely resembles, let's make the arrow this way. Okay. But the structure on the left is sort of not the whole story. That's not what the real molecule actually looks like. That resonance structure off to the right, plus the one that's similar to it with the double bond on the other chlorine, those are going to contribute some to the overall molecule. Okay? Which means that overall, the real molecule is going to have sort of less than a full double bond here. And it's going to have a little more than just a single bond in there. Okay? But it's going to more closely resemble that structure. Okay? So let's go to the next page where we sort of write that out a little bit. The major resonance structure, sometimes called the best resonance structure. It's generally the one that has the fewest formal charges. Okay? And that just means, especially if we have one with no formal charges at all, okay, that generally means the atoms are bonded in the way that they would normally like to be bonded in. Okay? If we're ever choosing between two that have the same charges, okay, the better resonance structure, we're going to look at where the negative formal charge is. Okay? It's better to have a negative charge on the more electronegative atom. Okay? Electronegativity means that the nucleus of that atom is pulling electrons towards it. So that negative is going to be happier on an atom that can pull minuses towards it more. Okay? So that's what we're going to be looking for also, and we'll get a chance to see that in a second. So let's just redraw what that major resonance structure was. Okay. For COCl2. It was CO double bonded. Okay. Get to the octet on the O. Get to the octets on those chlorines, but single bonded. Okay. This is the one that has no formal charges. But there's a structure we can draw. Oops, lost our. There we go. There's a structure we can draw called a resonance hybrid. A hybrid is just a combination of things. You see that in, every kind of agricultural crop that is created now is a hybrid of various other ones that have certain disease resistance and certain pest resistance and certain production characteristics. They crossbreed them together to make a hybrid. Well, that's sort of what a resonance hybrid is. It's kind of the combination or crossbreeding of all the various resonance structures that we can draw. But it's important that that be weighted based on which of those resonance structures is the major resonance structure. So if we take what we had on that last page here and sort of combine them together, let's just start with the atoms, the C, the O, the Cl, the Cl, okay? They all have at least a single bond, okay, to them. What we can do, though, since in the major resonance structure this was a double bond, but then in two of the minor structures that was just a single. Let's draw a dotted line right there, indicating that we're somewhere in between a single and double bond. Okay? And then we're also going to draw dotted lines over here, even though it's sort of unbalanced. Okay? The major structure had that single. Okay, so these ones are actually closer to single bonds. That one's actually closer to a double bond. But what we're actually going to do now is write in the partial charges based on where those formal charges were in the minor resonance structure. Right? No formal charges here. Minus, plus in this one. There's another resonance structure with a plus over here. So we're just going to call those partial charges. We're going to call this partial minus, partial plus, and partial plus. Okay? Those partial charges can come from minor in a resonance hybrid. Okay. Let's just, I mean, there's no official way of writing this, so let's just make a little notes, a couple little notes here. This is closer to a double bond, right? These two are closer to single bonds. In the end, we'll talk about actual characteristics of double and single bonds. Turns out their lengths are different. Double bonds are shorter. So the CO bond is going to be close to the length of a normal double bond. Okay? It's going to maybe be a little bit longer. Okay? The CCl bonds are going to be a little bit shorter than a normal single bond would be. Okay? Because for all of those, we're in between what a normal single or double bond would be, but we're closer in range to sort of what the major resonance structure showed us. Okay? So does anybody have any questions about that? These resonance hybrids, they're not things we have to draw very often, but sometimes we see them as a useful way of rationalizing how a molecule behaves. Okay? And you could certainly be asked questions about that, like based on the minor resonance structures where the partial charges would be. Or based on the minor resonance structures, how would you expect the length of a certain bond to be? And we'll answer some questions like that at the end too. Okay? So let's think about N2O. It says 16 valence electrons total. Where would that number 16 have come from? I mean, I gave that to you as a convenience, but I probably could have had you figure that out. Just from that formula right there, where would that number 16 have come from? Yep, 5 plus 5 plus 6. That's something that you need to do. And a lot of students get sort of confused about that. I've seen many students that will draw out a structure, oftentimes a totally wrong structure, then count out how many electrons they happen to use in that structure and then claim that that's the number of valence electrons. That's kind of missing the point. What we really need to be doing first is taking that formula, taking the existing number of valence electrons that those atoms have, right, just by counting 1 through 8 across the main group of the periodic table, right? So 5 plus 5 plus 6 equals 16. That gives us something we can actually check against after we've drawn a structure. Okay? So that's sort of an unbending rule that we need to make sure that our structures actually obey. Now, there's a lot of ways to draw N2O, right? And in fact, there's 2 major skeletal structures, right? The skeletal structure is just kind of what atoms connected to what. So what would be one way of arranging those 3 atoms? What do you think? Somebody just call something out. Just a skeletal structure, just one, the order of those atoms. O with 2 ends off of it, so something like that. And let's just put them all in a line because we got a lot of structures to draw. Okay, so that would be one option, which I assume is what you were describing. Okay, what would be another way that those could be connected? A triangle with the ends connected. I'm going to put that one sort of down here. Okay. Anything else? There's another major skeletal structure that we need to be thinking about here. NO. Doesn't always have to be symmetrical, okay? everybody understand how, with even a simple molecule like that, we have different ways that those atoms could be attached? Now what we're going to do is we're going to fill in electrons, and we're going to use formal charge as a way of assessing what the most likely molecule here actually is, what the most likely structure of that molecule is. Okay? So what I want you to do, there are at least 2 resonance structures of NON. Okay? There are at least 3 resonance structures of NNO. Okay? So starting from a skeletal structure and knowing that we need 16 total, what were the steps that we did last time? Sort of that all-purpose method for drawing structures. What did we do first? If I have just kind of starting with just all single bonds, and if I know the total is 16, what could I do? Yep, let's fill in dots. Put those dots in pairs, but you have to stop when you get to 16, and these bonds count as 2 each, right? So you've already got 4 on all of these structures, okay? So start drawing dots, and you can kind of draw them wherever, okay? Especially in small molecules like this. Normally we would kind of start around the outside, okay? Stop if you either have an octet, or stop if you get to 16 total, okay? But remember, in these straight ones, you're starting with 4 at least. So if you've drawn dots to get up to 16 electrons total, but then you still have something that is short of its octet, then what do you do? What can we do with our existing electrons to give more atoms access to those? Yep, we can move those dots to in between atoms to make double bonds or even triple bonds out of them. Okay? So why don't you see if you can draw 2 valid resonance structures of NON. See if you can do 3 of NNO. Okay? All will have full octets. And that's important. So let's take a few minutes. My only rules to you are that you need to have 16 electrons and the octets need to be full. But start with the dots. You're going to run into trouble if you try starting with double bonds or triple bonds. Okay? Start with the dots, then shift them around or something if it looks like you're short of an octet. What would be the problem with having this as part of your structure? An O, 2 double bonds on either side, and 2 dots. What rule have we violated? Okay, don't violate the octet rule. Okay. So if you've drawn a structure, look at every atom to make sure that every atom has 8 electrons, either as dots or shared in part of those bonds. About 12 on that O right there. Once you got most of them, check with your neighbor to see if you got the same ones. I think you don't have octets then on either of those ends. You just got 6 on those ends. So maybe fill one of these with an octet and use multiple bonding to fill the octet of the other one, maybe, or something like that. There's actually 2 of the triangle one that you can try if you get that far. Can draw another one. It's one of those that's obviously going to be better than the other, but no, just 2. What would be the third one, do you think? Yep, that's the same as that one. Yep, by symmetry. Now, once you've got all or most of your structures, start putting formal charges on those atoms. Remember, start with the valence electrons of the atom and then count backwards for every mark that you see around that atom. Could somebody describe for me what the bonds look like in one of your NON molecules?
Double bond between the double on both sides, and then both ends have 4 dots.
Okay. Does that have octets on each atom? 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Yes. Does that add up to 16? I think so. Okay. What's the other one? What do the bonds look like on the other one? Triple and a single? Then it must be 2 over here and 6 over here. Okay. What's kind of interesting, and if any of you go on to take more chemistry next year, if you go on to take organic chemistry, what that's all about, what you'll spend a large amount of your time doing is shuffling electrons around from one resonance structure to another. So what you can actually do, this lone pair right here, if I move that into there, if I draw an arrow showing where that lone pair is going, that'll make this one, and then that will overload that O, so it'll push one of those pairs out onto that N. So drawing those little curved arrows to go from one resonance structure to another. If you end up taking more chemistry classes, that will That will be a major part of it. But also, if you're stumped on trying to draw one resonance structure from another, you can think of doing things like that too. You can start with a pair of electrons, move it in between a couple of atoms. That will usually exceed the octet of that second atom, so you'll usually have to push something away from that. Okay? But that's one way of thinking about that. Okay? What are the formal charges here? What are these double bonded ends? What formal charge do they have? Anybody figure that out? Yep, the double bonded ends are -1. And the O is what? Yep, 6, 5, 4, 3, 2. What do you notice about those three resonance structures in total for that molecule? Mathematically, what do you notice about those three numbers that we've written there? They cancel out. Yep, they add up to 0. N2O is an uncharged molecule, and whatever your formal charges are, they need to add up to the overall charge of your molecule. So that's a good problem-solving, double-checking thing that you can do. Okay? In fact, if you've got two of the formal charges you should be able to figure out the third one just based overall. Okay? So what about the triple bonded N down here? 5, 4, 3, 2, 1, 0, right? And then the O with 4 bonds. What do you think? 2 plus 2. N with 1 bond. -2. Okay. Plus 2, -2. Alrighty. So now we have the option of 3 resonance structures over here. They're going to look very similar to the resonance structures over here. If you got the same number of electrons and the same number of atoms, you can draw pretty much the same bonds and dots. The only reason we have 3 over here instead of 2 is because this was symmetrical and this is not. Okay? So the symmetrical one, okay, with the 2 double bonds, will look pretty much the same, like that. We'll have triple bond on one side versus triple bond on the other side. Okay. 6 on the single bonded one, 2 on the triple bonded one. Okay. But in all cases, that's how you fit 16 electrons into 3 atoms, with everything getting 8. Okay? Those are really the only 2 rules. It's kind of a mathematical puzzle. You need that total number of electrons, and you need each atom to have access to 8. Okay? So we can start duplicating some of our efforts here, because we had a double bonded N, which is still going to be -1. This N with 4 bonds, now in the middle, what formal charge will this one have? Plus 2. 5, 4, 3, 2, 1. I got plus 1. If we start with 5 and then subtract 4 from that, essentially. That makes sense? Okay. And then O with 2 bonds is 0. That's like a regular O. Okay. And here's like a regular N with 3 bonds. Okay. That's a 0. Right here. There's another N with 4 bonds. That is a plus 1, right? 5 minus 4. Here's a minus 1. Okay. 6 minus 7. Let's take another plus 1 in the middle here. 5 minus 7, right? Minus 2. 5, 4, 3, 2, 1, 0, minus 1, minus 2. Okay. And then this must be a plus 1. Check 6, 5, 4, 3, 2, 1. Yep. Okay. So, did anybody figure out the 2 triangle structures? it's a good exercise, but what do you have to do in at least one of those triangle structures?
Double bond to nitrogen.
Yep. If you do the double bond, that would mean we need a pair on each nitrogen to get to 8, 2, 4, 6, 8, and then 2 pairs on the O. Okay. And the other resonance structure would just be maybe that double bond between one of the other two. Right? You could do either of those two. They're the same, okay, by symmetry, but something like that. Okay. 5. So n minus 1, O plus 1 looks like. What about the formal charges in this one? Yep, these are all 0. Okay. So if our task were to draw all possible resonance structures for N2O, okay, in all possible ways that those 3 atoms may be connected, I think we've done it here. Topologically, there is no other way to attach 3 atoms. Okay? That just means hooking things together in a physical way that they can be connected. Okay? Now, the question becomes, which is the most likely structure of that actual molecule? Okay? So, the one with all 0, from an electronic perspective, okay, meaning from position of electrons, that all zeros, that one with the triangle with the double bonded ends there in the middle, that's the one that has the most normal bonding patterns for all of those atoms. So in terms of electrons, okay, that's the one where those would be bonded the most typical way. However, it turns out we're going to learn in the next chapter that bonds only happen over certain angles. Okay? And an atom that has a double bond and a single bond to it, those are going to want to be about 120 degrees apart from each other. Okay? We're going to do molecular geometry, but this thing, the pair, and that thing are all going to want to spread out around that. Whereas here, they're closer to like 60 degrees apart, more like a triangle. Okay? So I'm going to give you a pretty important rule of thumb here, that while electronically that's fine, okay, we're probably going to have to avoid rings in inorganic molecules. That molecule right there is going to be very, very high in potential energy, just because in order, and you know, if you've ever done stuff with those model kits, we'll be able to do stuff with that maybe later, but you would have to squeeze those things together and they still wouldn't quite fit just right, okay? And one little tap and the whole thing will just come flying apart again, and that's pretty consistent with how actual molecules would behave like that. The electrons just aren't in the right place to be made in that kind of structure. So, while electronically, yes, our bonding pattern is fine, practically, talking about the bond angles, that is going to be a very, very high energy, very unstable structure. Okay? So, it was a good exercise for us, especially because we can find one here with all the orbits filled, but I think we can pretty practically eliminate those rings. Inorganic molecules, what does that mean? Anybody know? Yeah. So carbon, organic and inorganic, that has to do with the presence of carbon. Okay? Carbon can form rings. And does all the time. organic molecules, carbon, because it makes 4 bonds, it can make big long chains and rings and complex structures and stuff like that. Okay? And carbon's bonds to itself are strong enough that it can do that. Other atoms, not so much. They have much weaker bonds, and they really cannot overcome the strain required in getting those rings together. Okay? So for us, if you take 1062, we'll have a chapter on organic compounds. We'll talk all about the rings and stuff. But for inorganic compounds, compounds that are not carbon-containing, we're probably not going to have rings. Okay? So we're probably limited to the sort of open chain arrangements like that. All right. So tell me the rule that we had up above that helped us decide which is the major resonance structure. What are we going to look for?
Negative charge and a more electronegative atom.
Yeah. And even before that, we're going to look for the one that has the fewest formal charges. Okay. I'm also going to add something here. And lowest magnitude. Okay. Because a molecule that is -1 plus 1 will be much better than a molecule that is -2 plus 2, for instance. Okay? If we have no other choices. Okay? So we're going to kind of look at both. We're going to look at how many formal charges we have, and we want those formal charges to be as small as possible. Okay? So that can pretty much eliminate any of those that have 3 formal charges, correct? So that first one, this last one, three. Okay. And then we're left with a couple that have 2 charges, okay? +2, -2, +1, -1, +1, -1. We're going to probably eliminate the one with the +2, -2. Okay. That has 2 larger charges. That's supposed to be a parentheses there. Okay. Right? So we're down to the 2 then that are just +1 and -1. And that's when we look at electronegativity. So based on that rule of electronegativity, which atom do you think it would be better for us to have that minus charge on, the N or the O? What do you think? Electronegativity goes sort of by the periodic table, right? What's the most electronegative of the elements? Okay. So whatever is closer to fluorine is going to be more electronegative. Okay, so that means O is more electronegative than N, correct? So which one here do you think is our major? Going to need a new color here. The double bonded one, that has the minus on an N. This one has the minus on an O. That's what we're looking at. So what do you think? Yep. The better structure has the minus on the more electronegative atom. So that's right here. Okay. There you go. So minus on the more electronegative atom. All right. So it turns out N2O, it can exist as NON and NNO. NNO is a lower energy, more stable molecule. Okay? And the actual structure of NNO most closely resembles that resonance structure we drew there in the middle, although it'll be a hybrid to some extent of all of them. Okay? So, does that make sense? So, we can use formal charges for a couple of things. Choosing between structures to figure out which is the more stable structure. Okay? We can do that with formal charges. And then within a structure, figuring out which of those resonance structures will most closely resemble the actual molecule. Okay? So, questions about that? Yeah, that's a nice little exercise that we can go through. Okay? In many cases, it will, this was one where you had very little information to go by. In other cases, and especially if you got some H's in there, that helps with figuring out what the skeleton structure is, because H just makes one bond and it's always on the end. That will help you. Okay? That cuts down dramatically on the possible arrangements and the possible resonance structures. Okay? But if you get a question that's either draw the major resonance structure or draw 4 resonance structures and indicate the major or something like that, those are all things that you could be asked to do. Okay? So, questions? But again, that's something you probably need to practice a little bit, just so that you make sure that you can, look the right places, that you can go the right directions with things, and take the things as you go. Okay.